Thank you all for joining. I'll tell you that this talk is more about the application semantics. So you're running in, what's happening inside of the application. So hopefully that is why you're here. So my name is Cornelia Davis. I am going to talk to you today about cloud native patterns. So let me introduce myself. I know a little something about cloud native patterns. I've been working in this space for, the last 15 years or so. I spent quite a number of years working on Cloud Foundry, really developer platform, and I wrote a book. So Manning approached me and asked me if I was willing to write a book, and I wrote a book on cloud native patterns. So the title of my talk is Rethinking Cloud Native Patterns, and so you're going to see how my mind shift has changed over the course of the last several years. These days, I'm a developer advocate at a company called Temporal. Does anybody know Temporal? Awesome. There are at least a handful of you. For the rest of you, you're going to be like, why did I not know about this? Because it is like the best kept secret in cloud native applications these days. So you're going to learn all about it today. So we're going to do a quick level set some context. Then we're going to do a little bit of studying, and then we're actually going to drill into the weeds. And so I went back and looked, and I think I put down beginner and intermediate for this talk. So the first half of it is more beginner. We are going to look at a little bit of code, and I am going to give you a demo. So on that level setting, in the days of old, and I can see it up there. So I've been doing this long enough. Does anybody know Documentum? So I worked on a couple of people, at least one person. So Documentum was a software that was built back in the 1980s, I think, and it had this type of architecture. It had a big old database, it had a big old server tier, and then it had the UI tier. If something went wrong in the database, then we at Documentum could shrug our shoulders and say, wasn't our fault. And you know what? Our customers were okay with that. They were like, it isn't your fault, it was the database. We'll go after Oracle, we'll get on them. And we used to count the number of days that we kept applications running. So it was like, oh, the application has not cycled in 273 days. And that was a good thing. We know that's not the case. We're here at Kubernetes Community Days. We know that, I think I've heard things like containers stick around on average for minutes or hours rather than certainly not days or months. But that expectation of stability, and I've been in the software industry long enough, that expectation of stability determined what our architectures looked like. So we built architectures like this where we did things like we kept state in memory. Because you know what? When we were going to cycle to a new version, we were going to do that very, very carefully, and we were going to go through a number of steps to preserve that state, kind of take a long maintenance window, bring up the new thing, and then we'd bring the state back over there. And even as our architecture started to change and we started to get a little bit more horizontal, we still made that assumption of stability. So those instances were going to stay alive for a long time, and we did things like we built sticky sessions, right? That was a pattern that we used to make sure that when subsequent requests came in, they were going to go to the same instance because that's where your local state was. But things evolved. We're here at Kubernetes Community Days. We now have architectures that look like this. We're serving traffic to one server. That service goes kapooey, and so no problem, we will just go to the next service. And we love Kubernetes, because without Kubernetes, or I mentioned, I didn't talk about it, but I worked on Cloud Foundry for a while, so that was kind of the precursor of Kubernetes. Without technology like Kubernetes, even this would be hard, because Kubernetes takes care of things like bringing that blown up instance, taking it off of the network, bringing it back. Kubernetes takes care of all of that for us. So that's a really wonderful thing. And in order to do that, developers, and I put that in quotes because I don't know if it's the developer or the platform engineer or the DevOps engineer, they had to learn a whole bunch of patterns. They had to understand what happened in that application topology. And things like taking a look at these leaders in the Kubernetes space, their book. But here's the thing, I suggest that Kubernetes is more about the application topology. It's about keeping your application topology healthy and doing things like rerouting stuff, but it doesn't go inside of the application at all. Sure, there's things like, the health checks and it integrates all of those things, but it doesn't take care of the application semantics. So what about those application semantics? Well, what did we do in the last 10 or 15 years? Well, developers had to learn a whole bunch of patterns, and I know something about that. I wrote a book. This is the inside cover of the book. These are all the different patterns that developers had to learn. They had to learn about things like retries. They had to learn about externalizing their state. They had to learn about event-driven architectures and event sourcing. They had to learn about circuit breakers, all of those different things. And the developer was responsible for either implementing or using a framework to implement those patterns so that, because it's no longer okay for us to shrug and say, oh, the infrastructure went down, not my fault. It is your fault. You have to keep your applications more stable than the infrastructure it's running on itself. And so but because of all of these patterns, our architectures and our bill of materials got way more complicated. So let's take a simple use case here, which is we're going to do some order processing. An order's going to come in, we're going to process the payment, we're going to email a confirmation to the user who just purchased that product. We're also going to, in parallel, because this can be asynchronous, send a notification off to the warehouse to do shipping, and once the shipping is underway, we're going to send another email to the user, right? Pretty simple application. But how do we have to build that? Well, here's the basic idea. My payment processing, that's going to happen synchronously. Well, if I'm doing that synchronously, one of the cloud-native patterns is I need to wrap retries around that because the network could be down. But if I wrap retries around it, then, oh gosh, I better put a circuit breaker in front of that service because otherwise I could accidentally DDoS myself, right? Now, that asynchronous stuff, the email and the shipping, we're going to introduce Kafka. So Kafka, and we're going to introduce a topic. So we're going to put that message out on the topic, and then email confirmation and shipping is going to pick that up. But hang on, I have another email that can't happen until after the shipping happens, which is asynchronous. So I'm going to introduce another topic. And by the way, you'll notice that some of my logic that was over in the order processing kind of moved down here into the lower right-hand corner. So it's actually implicit, that relationship between the shipping and the shipping email confirmation, that's kind of implicit. It's wired up in the way that I've wired up this topic or this queue. Oh, and of course, I need to introduce Redis as well, because I need to manage my session state, and that's going to go to an external service. So these are all the patterns that I just showed you in that really simple example that you have to implement. You're doing a request response because you need some synchronous stuff. You're doing retries and circuit breakers. You're doing an event-driven architecture, and you're managing state. So that's an awful lot of complexity for the developer. What I want to introduce to you today, and what I'm going to talk about here, is entirely open source. I work for a company that has a hosted service, a SaaS service of this, but I'm talking to you only about the open source project. And what it does is it allows you, the developer of the cloud native application, a new programming model so that you don't have to implement all those patterns yourself. You adopt this new programming model and it does it for you. So I'm going to introduce you to this project called Temporal. So it allows the developer, and I'll show you some code in just a little bit, to program the happy path. And that complex architecture that you saw with queues and retries and circuit breakers and all of that stuff, Temporal sets all that up for you. It's not that those architectures are bad. Those are the architectures that allow your systems to be more resilient than the infrastructure it's running on, but you don't have to build them as a developer. The technology comes as a service as well as an SDK, and that SDK lives with your code. The SDK is available in all of these different languages, so if you want to program in Python or Go or Java, I'm a Java person, or any of these other languages, you can do that. It's mostly MIT licensed. The only thing that is Apache licensed is the Java SDK, but pretty much everything else is MIT licensed. We do not do open core. It is the entire thing is open source. There are no other features that are sitting behind like a proprietary firewall. So what I want you to do is I want you to think of Temporal as another kind of backing service. But it's not doing state management. Well, actually it is. It's doing a whole bunch of things. But think of it as a backing service that is about resilience. It's going to give you resilience as a service. That's the punchline. So we're going to take a specific example like state management, and we're going to dig into the weeds here a little bit, but we're going to take a simple example here. So if you, the developer, are responsible for state management, you've got some local state on that left-hand service, you've had to store that into this Redis, into this backing service, so that when it goes on fire, we can reconstitute it in the next service. The picture here with Temporal is the same in that we have a backing resilience service right here. That can go up in smoke, but here's the thing. In the red up there, it says Temporal is responsible for that protocol, for the resilience protocol. So how on earth does Temporal do that? Well, notice the little orange that is attached to each one of the services. That's the SDK. So the SDK is what's implementing those protocols. It's implementing retries and circuit breakers and event-driven protocols. It is what implements all of that. And so here's drilling into it a little bit more. So what you do if you're writing a Temporal application is you write your business logic in any one of those languages that I talked about. You leverage a couple of the abstractions that are part of the SDK, and when we get to that point in the code where we hit one of those abstractions, the SDK does the communication back to the Temporal service. That's basically how it works, and we'll go into some of the details in just a moment. So I keep promising that it does all of these resilient services, and it looks a little like black magic, right? So I want to go into the details in just a moment. So we're going to take this preservation of application state, and I'm going to go through it in detail so that you can see a little bit of the magic that's happening behind the scenes. So again, what we want is this behavior. I want to manage my state. So I want to externalize the state, but I as a developer don't need to write that. And I'm going to show you the code in just a bit. So here's how state management works with Temporal. It preserves your application state for you so that if your application process goes away, it reconstitutes it in the new node. Now, when I first started learning Temporal, I posed a number of questions to myself. And I said, okay, great. So yeah, it's doing that state preservation that you see there. So I was like, okay, what state is sent? Is it really every single variable in my code gets sent down to the state store? Surely not, I thought. And I was right. What format? Is it serializing that state? Is it taking those variables and creating a JSON payload or some kind of serialization? Or is it taking memory snapshots? And I thought, memory snapshots? Nah, can't be doing that. It doesn't. And how often does it do it? Does it do it on every single variable, every single instruction? What did I say? Surely not. And it doesn't. But I am going to show you how it does work. So let's think about programs for a moment. Remember I said that it's a slightly different programming model? So here's the main thing that you need to think about if you're using this programming model. You think about your application, and there are predictable parts of that application. like x equals y times z. Every time I multiply y and z, I'm going to get back the same value, right? So that's predictable. And then there's less predictable parts, like getting a value from the user. One time the user could give me the value 10, the next time they could give me the value 20. So that's less predictable. And so if we take this application now, the developer, the way they need to think is they need to think about, okay, here are the less predictable parts. Here are the parts that if I run it one time and the next time it could be different. And I need to identify those. Now, I'm going to ask you to suspend disbelief for a moment because all I/O is unpredictable. And of course, enter the print statements there are technically I/O. But just for simplicity's sake, let's just take the reads as the less predictable parts. What you do is you take those less predictable parts and you wrap them in an abstraction that we call an activity. Okay? And that's where the SDK comes in. The SDK sees that activity and it says, you're doing something with state here, and I need to implement this protocol. I need to implement the protocol that's giving me resilience for distributed systems. So let's step through this example. We've got my app that's running down here in the lower left, and I've got my temporal server. The temporal server is where we're going to preserve that state. So I print, enter y. I get to the next line, and I ask the user for input. And let's say that the user inputs the value 4. Remember I said that the SDK says, you're doing an activity here. And so when the user has entered the value 4 and the activity returns, the SDK says, all right, I've got to take that value. Remember I posed the question of which values am I storing? I'm storing the responses to these activities. So the result of the less predictable part. So I'm storing the fact that the user entered the value 4. And it sends that up to the server. Then it continues on, and let's say that right here, that service crashes. But I want to continue this on the next node. So what do I do? So the activity returned 4, but there's another piece that I haven't told you about. In addition to storing the result of the activity, Temporal also stores an event history. So it keeps track of where you are in that execution. So it, for example, stored the fact that you started the application. It recognized when an activity was invoked. It recognized that the activity completed. And at this point, my old instance blew up. But all of that stuff is stored on the service. So now when I get to the new application, the way that we reconstitute the state is we just run the application over again. The predictable parts, those are going to happen the way that they did before. The less predictable parts, we have the results. The results are stored. So what we do is we replay the logic. We start at the top and we say, great, print, and that's why I ask you to suspend disbelief, because maybe you don't want to print that again. But at this point, I say, look, I already executed this activity. I'm just going to retrieve the value from it. So I get back the value 4 that is going there. Now I've exhausted the event history, and I just keep running. State management. I will show you the code. So here's the punchline. Temporal, when it comes to state management, preserves just enough state to reconstitute your state in the new instance. So that was stateless services. These are some of the other things that the protocol implements for you. It does retries. It does event-driven architectures. Those are all things. So let's go back to our example here, and I'm going to show you, I have time for my demo. So remember, this is the simple order processing example, and this was the Rube Goldberg machine that I had to create to satisfy it before, right? This is what the code looks like in Temporal. So what you can see here is at the very top, I'm making a call, synchronous call to the process payment. It looks like a synchronous call, but I'll tell you behind the scenes, it's actually doing it asynchronously because that's part of the way that it can do these things. You'll notice that each one of these is happening within an activity. Then you can see that I'm in parallel, just making a call down to the order email, the email sending and the shipping. Then about the middle of the thing there, you see that ship order input .get. It's invoking that promise. So it says, don't send the confirmation email of shipping until after I've shipped, until I heard back from the shipping. And in this particular case, I also said, well, we're not going to actually close this entire application until I know that the emails have both been sent. Okay? So basically, this is what my code looks like. No Rube Goldberg machine. So I'm not responsible for implementing that. So rather than taking a moment to summarize, I want to show you a quick demo. So this particular application, I have it mocked up here. Here's my payment details. So I'm going to submit an order. When I submit that order, I'm going to come over here and I'm going to show you that executing. So it is a live demo, so let the demo gods be with me. And so what you can see here, if I scroll down, is it invoked all of the steps that I just talked about. Processing the payment, then it shipped the order and sending email in parallel, and then after the order was shipped, it sent the second email. Now I want to show you another demo of this because I want to show the resilience. If I come back to the payment form and I submit the order again, I'm going to come over here and I am going to kill this. Okay? So I've killed my application. If we go back to the display that we have here, and again, this display, everything is open source, all open source. So you can see here that my application is running, and if I scroll down, you can see that it processed the payment, and it sent the confirmation email, but the process died before I got the shipment out. So you can see there, it's trying to ship the order, but notice that it says attempt to. Those are the retries. It's doing the retries. You didn't see retries in my code. It's all happening for me. Now let me bring this application instance back. So now I'm going to be Kubernetes. Oh, I recognize that the app instance went down. Let me bring up a new instance, start running, and let's watch what happens here. Now, my retries, just like you normally would with retries, has a back-off coefficient. So depending on how verbose I was just a moment ago, it may take a moment. There you go. So in the next retry, it said, the service is back. These retries are implemented at the server level. So even if my application dies, my retries don't die. The retries are happening at the temporal service. That's where all of the resilience logic is. So you can see that it took a long time to ship that order because the instance was down, but when the instance came back, it just worked. Now, a couple of final things that I want to tell you about. So I'm not going to go through the summary slide in detail. What do people use temporal for? Microservice orchestration, like we talked about here. Async processing, we saw an example of that. Long-running processes, and by long-running, I don't mean minutes or hours, I mean days, weeks, or months. So these processes can be running for a very long time. We also have mechanisms for human in the loop so that you can inject things into those long-running processes. And it just so happens that temporal works really great for AI agents because you oftentimes have to orchestrate a lot of things. There's a lot of value in this. There's developer productivity, operational productivity. We call some of this crash-proof execution. I mean, this is the Kubernetes community. We know what crash-proof, the value that can bring. But here is the slide that my sales and marketing colleagues would want me to start with. But I'm a developer, so I want to talk about the tech first. But temporal, who uses Snapchat? Okay, there's a few people. I was going to say, maybe this crowd is a little bit more mature than that, but every snap goes through temporal. Have you ordered Taco Bell online recently? You've used temporal. Every DoorDash order goes through temporal. Every Airbnb booking goes through temporal. Netflix, who I consider the poster children of cloud native architectures, they were the ones who designed a lot of this stuff. They have the whole Netflix suite. They use temporal in there to back Spinnaker. And here's a big kicker. Has anybody played with Codex? So OpenAI's recent announcement on their coding agent, it uses temporal. So this is a really well-kept secret that, as a developer advocate, my job is to make sure is no longer a well-kept secret. So with that, I am 51 seconds over, which is not too bad. I'll step out into the hallway. If anybody has any questions, I want to make sure that I give the next speaker the stage. So thanks so much for your attention, and I'll be around a little bit. I'd love to answer any questions. Thanks.